This video focuses on models that describe the structure and evolution of the universe. They are known as cosmological models. Cosmological models must satisfy two important scientific concepts, namely the cosmological and Copernican principles. The cosmological principle is the notion that the matter and energy in the universe is uniformly and isotropically distributed when viewed on a large enough scale. The Copernican principles state that observations made from any location across the universe are the same. It is a well-known scientific fact that our universe is expanding, but this expansion occurs in a very special and peculiar way. Edwin Powell Hubble was born on November 20, 1889 in Marshfield, Missouri. He played a crucial role in establishing the fields of extragalactic astronomy and observational cosmology. The Space Telescope launched in space in 1990 was named in his honor. In 1919, Hubble was offered a staff position at Mount Wilson Observatory, near Pasadena, California. He worked at Mount Wilson until his death in 1953. Hubble discovered that faraway galaxies appear to be moving away from each other at speeds that are proportional to the distance between them. This discovery became known as the Hubble's law. In this equation, r is the distance between galaxies, v is the receding velocity, and the constant multiplying the distance in the right-hand side term is the empirical Hubble constant. From his measurements, Hubble determined the value of Hubble's constant to be equal to 0.0692 per billion years, which is the same to say that the distances between galaxies increase at a rate of 6.92% per billion years. This expansion is in direct contradiction of the view of the Big Bang as an explosion. The way the universe is expanding is like the way a loaf of raisin bread rises in the oven. As the dough grows, so does the distance between the raisins. If the dough doubles in size in all directions and in all locations, raisins that are 1 inch apart becomes 2 inches apart, raisins that are 2 inches apart becomes 4 inches apart, and so on. From the point of view of an observer located on a certain raisin, it seems that all other raisins are moving away from it. The separation of the raisins comes from within the bread dough between the raisins. The universe has expanded since the Big Bang, and it is important to understand that the universe is not expanding into space, and there is no need even for space to exist outside the universe. The term Big Bang may give the impression that the universe started to expand like an explosion, and this is not true. For a generic observer A, we can define a coordinate system, in which the current distance from A to an observed object is measured as if A is at rest. This coordinate system is fixed, it is not expanding, and the distance measured is called co-moving distances in cosmology and is denoted as r sub c. The only way to measure distances between the observer and a faraway object is by measuring some property of the light that left the object towards the observer. However, when light left the object towards the observer, the distance between them was different than the current comoving distance. As light travels through space, the distance remaining to be traveled is continuously expanding and affecting the arrival time of light at the observer position. This distance between observers at a certain cosmological time in the past is called the proper distance in cosmology and is denoted as r sub p. The proper distance is a function of time. This is a pure theoretical concept. We cannot observe where an object is now nor where it was in the past. But if we have a cosmological model describing how the universe expands, we can calculate those positions from observations from the light that left that object in the past and is reaching us today. For now, the important concept to remember is that co-moving distance remains fixed since it expresses the current distance to the observer. The proper distance is the distance at a certain point in cosmological time. It is related to the comoving distance through the introduction of a scale factor that is a function of time. The scale factor is represented by the letter A. The relationship between proper and comoving distances and the scale factor is: the scale factor A is defined as 0 at the Big Bang and as 1 today. The recession velocity is the rate of change of the proper distance with time, or in terms of the scale factor and comoving distance, which can be rewritten as defining h as, we can write the recession velocity equation as the recession velocity can also be written as a function the parameter h, the scale factor a, and the comoving distance as we normally use the subscript 0 to denote today's conditions. For today's conditions, the receding velocity is expressed as, since by definition the scale factor today is equal to 1, we have. This last equation is what Hubble obtained. If we know how h changes with time, we can determine how the scale factor changes with time, and we can calculate proper distance at a past time for any comoving distance today. This is the purpose of cosmological models. It allows us to describe how the universe expands and determine current, past and future distances across the universe. Newtonian mechanics is not an adequate tool to simulate the evolution of the universe. However, it will be presented as a stepping stone. The mathematics of Newtonian cosmological model is simple and allows us to become familiar with important concepts and terms that appear in more accurate and sophisticated cosmological models based on Einstein's general relativity theory. Let's imagine a uniform universe with a uniform matter density. Let's analyze the expansion of a spherical shell containing part of this universe with proper radius rp. The shell thickness is delta r. As this spherical shell expands, so does its thickness and no matter crosses its boundaries. Therefore, the mass of objects in the shell is constant and equal to delta m. Assuming a uniform universe, the combined gravitational force acting on the mass of objects on the shell is equal to the gravitational pull of all matter inside the sphere as if it was concentrated on its center. The forces from the homogeneous universe outside the shell are cancelled out. The total energy of shell is made of the potential energy delta T and the kinetic energy delta K, where capital M is the mass inside the sphere. The total energy for the shell delta U becomes, which can be rewritten as, the mass M can be related to the current density based on the comoving sphere radius as, which when replaced in the previous equation yields. Now using the definition of the scaling factor, we can write the first two terms are functions of time. The last term involves the ratio of the shell total energy to the shell mass. This ratio for a homogeneous universe is constant. This term also involves the comoving radius of the sphere we are analyzing, which is also a constant. This constant term can be written using a constant curvature parameter k and the constant speed of light in vacuum as. The left-hand side term is the Hubble's parameter, and the Newtonian mechanics cosmological model becomes. The left-hand side function h of t describes how the shell expands. The first term on the right-hand side is how mass concentration changes as a function of the expansion, and the last term is related to the energy content of the shell and its curvature k. For today's condition we can write defining Newtonian cosmological model becomes a function of the weighted average of two terms. The general solution can be obtained solving the system. After substitution we have And finally, solutions can be obtained if we know the contribution of the mass and curvature terms. We will now move to describe the equations for modern cosmological models based on Einstein's general relativity equations. Alexander Alexandrovich Friedmann was born on June 16, 1888, and died on September 16, 1925. He was a Russian and Soviet physicist and mathematician. He originated the pioneering theory that the universe is expanding, governed by a set of equations he developed known as the Friedmann equations. Georges-Henri Joseph Edouard Lemaitre was born on July 17, 1894 and died on June 20, 1966. He was a Belgian Catholic priest, theoretical physicist, and mathematician who made major contributions to cosmology and astrophysics. Lemaitre and Friedmann developed the first Big Bang model of the origin of the universe based on Einstein general relativity equations. The model has been modified into the lambda-CDM model, also known as the Standard Model of Cosmology. The lambda-CDM model equation is: it contains terms similar to our Toy-Newtonina model plus two additional terms. The term omega m is the density parameter related to both regular or baryonic mass energy and cold dark matter. The term omega r is the radiation density parameter, that is energy from massless particles such as photons and relativistic neutrinos. The term omega k is related to the universe curvature. The last term, omega lambda, is related to the dark energy density parameter. Baryonic matter refers to the ordinary matter that makes up stars, planets, and all visible objects. It is composed of protons and neutrons. Fritz Zwicky was born on February 14, 1898, and died on February 8, 1974. He was a Swiss astronomer and worked most of his life at the California Institute of Technology, where he made many important contributions in theoretical and observational astronomy. Vera Florence Cooper Rubin was born on July 23, 1928 and died on December 25, 2016. She was an American astronomer who pioneered work on galaxy rotation rates. The Vera C. Rubin Observatory in Chile is named in her honor. Dark matter is a hypothetical type of matter that only interact with normal matter and energy through gravity. Astronomers didn't even know dark matter existed until the 20th century. In the 1930s, Zwicky noticed that galaxies in the Coma cluster were moving faster than could be explained by the amount of matter astronomers could see there. In 1933, Zwicky was the first to postulate the existence of unseen dark matter, describing it as Dunkel Materie. It wasn't until the 1970s that U.S. astronomer Vera Rubin confirmed the existence of dark matter by studying how individual galaxies rotated. She uncovered the discrepancy between the predicted angular motion of galaxies based on the visible light and the observed motion. Her research showed that spiral galaxies rotate quickly enough that they should fly apart, if the gravity of their constituent stars was all that was holding them together. Because they stay intact, a large amount of unseen mass must be holding them together. Rubin's results came to be cited as evidence that spiral galaxies were surrounded by dark matter halos. Rubin's calculations showed that galaxies must contain at least 5 to 10 times more mass than can be observed directly based on the light emitted by ordinary matter. Rubin's results were confirmed over subsequent decades, and became the first persuasive results supporting the theory of dark matter. Scientists today think dark matter exists in a vast, web-like structure that winds through the whole universe, a gravitational scaffold that attracts most of the cosmos' normal matter. Scientists do not know exactly what dark matter is. There are currently several theories on dark matter's composition. Saul Perlmutter was born on September 22, 1959. He is a U.S. astrophysicist, a professor of physics at the University of California, Berkeley. Adam Guy Reese was born on December 16, 1969. He is an American astrophysicist and Bloomberg Distinguished Professor at Johns Hopkins University. Brian Paul Schmidt was born on February 24, 1967. He is an American-Australian astrophysicist at the Australian National University's Mount Stromlo Observatory. The 2006 Shaw Prize in Astronomy and the 2011 Nobel Prize in Physics was shared by Saul Perlmutter, Adam Rees and Brian Paul Schmidt for providing evidence that the expansion of the universe is accelerating. The first observational evidence for dark energy's existence came from measurements of supernovas. Some supernovas have constant luminosity, which means that they can be used as accurate distance measures. Comparison of this distance to the recessing speed shows that the universe's expansion is accelerating. Prior to this observation, scientists thought that the gravitational attraction of matter and energy in the universe would cause the universe's expansion to slow over time. Since the discovery of accelerating expansion, several independent lines of evidence have been discovered that support the existence of dark energy. During the 1980s, most cosmological models considered that the universe consisted of 95% dark matter and 5% ordinary matter energy. Modifications were needed to explain the experimental results. The cosmological constant, that was first introduced by Einstein to oppose the effect of gravity on the behavior of the universe, is now being used to account for dark energy concentration. The lambda CDM model then became the leading cosmological tool. The curvature term has to do with the type of geometry of the space-time. To better understand this, we need to use the simpler and more familiar problem, which is the geometry of a regular two-dimensional surface. A two-dimensional surface can be Euclidean, hyperbolic, or elliptical depending on how it is curved. The geometry type governs several aspects of this surface. For instance, in a Euclidean geometry, the sum of the angles of a triangle is 180 degrees, whereas in hyperbolic geometry the sum is less than 180 degrees, and in elliptical geometry it is greater than 180 degrees. The terms Euclidean, hyperbolic, and elliptical are replaced by flat, open, or closed when referring to the geometry of the spacetime. It is assumed that our universe on large scales is flat, although next to galaxies and black holes it may be curved differently. The mass-energy content of the universe is currently 0.05 ordinary matter, 0.268 dark matter, with a total 0.318 for omega m. Dark energy currently dominates the universe expansion, and this term is 0.68. The universe is assumed to be flat and the radiation component is only 0.002. The universe expansion is divided into several epochs depending on which matter-energy effect dominated the universe behavior. Assuming a flat universe, we can define the fractional contribution for each term to the lambda CDM model as the fractional contribution of each term can be represented in a graphical form as a function of the scale factor. The first epoch of the universe was the radiation-dominated era due to massless particles. This density decreases with the fourth power of the scale factor, and at a certain point, matter energy started to become more important. However, mass energy also decreases with the third power of the scale factor, and at some point, in the future we will be in a dark energy dominant era. We are currently in a phase where both matter and dark energy participate in the behavior of the universe expansion. The lambda CDM model can be solved using the following approximations for the current density parameters. The Big Bang model equations are the second equation can be written as Combining with the first equation yields that can be rearranged into let L be defined as, then we have integrating or using the limits of integration we obtain which can be solved for time t. Using the current value for Hubble's constant and density parameters, the age of the universe can be determined. The value of 13.8 billion years is what science currently estimates for the age of the universe. Using the Copernican principle, we can draw a generic frame of reference for an observer in our universe. We will place the observer at the origin of the position axis and at a time of 13.8 billion years after the Big Bang, as shown by the black dot. The distances to the observer are proper distances which are function of the cosmological time. The Big Bang is the black dot at the origin of the graph. The horizontal dashed line passing through the observer's position represents today's distances and therefore represents comoving distances. For a certain astronomical object, let's say a galaxy that is located at a certain comoving distance from the observer, the red dashed line represents this object's world line or the proper distances as a function of time. The intersection of this line with the horizontal dashed line shows the current comoving distance of the object to the observer. The object current position is represented by a red dot. The Hubble sphere radius is defined as the distance to the observer where the receding velocity is equal to the speed of light. A sphere around the observer with this radius is referred to as Hubble's sphere. The Hubble sphere separates two regions of the spacetime. In the first, the receding velocity of space is less than the speed of light. In the other, the receding velocity of space is greater than the speed of light. The receding velocity is the Hubble's radius in proper coordinates, can then be obtained from using the cosmologic model. We obtain this equation represents the Hubble sphere radius as a function of time and is plotted in the observer frame of reference as the continuous blue line. We are measuring distances in giga-light-years and time in giga-years, therefore the speed of light is 1. The current value for the Hubble sphere comoving radius is the Hubble sphere radius today is 14.45 billion light-years. Past light cone represents the location of all sources of light in the past that are reaching the observer today. In other words, it represents the proper distance for all objects that can be observed in the sky by the light they emitted in the past. The light that was emitted at a certain proper distance in a past cosmological time is traveling towards the observer. However, simultaneously the proper distance left to be traveled is continuously increasing. A change in proper distance at a time t can then be related to a change in the comoving distance as if we take this proper distance interval as the distance traveled by light in an interval dt, we can write this change in proper distance can be transformed into a change in co-moving distance that light has traveled in an interval dt. We can integrate this from today to the emission time to obtain co-moving distance traveled by light. Although this is a co-moving distance, it is not constant since it does not refer to any specific proper distance. It is the total co-moving distance traveled by light and incorporates the speed of light and the expansion of the space since the light was emitted. Therefore, it is a function of the emission time, Te. Using the cosmological model equation, the co-moving distance traveled by light becomes the analytical solution involves hypergeometric functions. Alternatively, the co-moving distance traveled by light equation can be integrated numerically to generate the past light cones, which represent the co-moving distance location of a source of photons in the past that are arriving at us today. Once the co-moving distance traveled by light has been determined as a function of emission time, we can calculate the proper distance traveled by time for a beam of light emitted at a past time Te. The stars and other celestial bodies in the sky are visible now because the photons emitted by them in the past are reaching us today. Their current co-moving position can be calculated, but we can't observe the photons that are being emitted now. Some of those objects may not even exist anymore. What we see is the past. The current light cone is a cross-section of time-space of the visible sky. We can now plot the past light cone in the observer reference frame. In this picture, the red circles represent the location of two celestial objects at the time they emitted the light that is reaching the observer today. The triangles represent their current position in relation to the observer. Two things stand out from this graph. The first is that the farthest light source in the past that is arriving at us today is located at a co-moving distance of 46.73 billion light-years. This is the visible universe radius. However, at that time the universe was very dense and photons interact with free electrons and atom nuclei. The universe was said to be opaque to radiation or photons. The universe became transparent to electromagnetic waves around 400,000 years after Big Bang. The radiation we see today as the cosmic background radiation is the oldest vestige of this early phase of the universe. The second thing that stands out is the fact that some points on the light cone lie in a region where the space was expanding at a speed higher than the speed of light. This may seem weird at first, but we need to realize that light is always moving in proper coordinates in time, and it can overcome the space expansion. The particle horizon is the distance reached by a photon originated in the observer location at the Big Bang. The co-moving distance traveled by light is which can be adapted for the co-moving particle horizon distance y as and we can determine the proper particle horizon as currently, the light emitted at the observer location at the Big Bang has reached a distance of 46.7 billion light-years. This is the same as the observer visible universe radius calculated before. Observers closer to that could see light emitted between the Big Bang and now, but those away more than 46.7 billion light-years have not received that light yet. However, the universe was opaque for about 400,000 light-years. The cosmic event horizon is the distance from where an emitted photon will never reach the observer. The co-moving distance traveled by light is which can be adapted for the cosmic event horizon co-moving distance z as and we can determine the cosmic event horizon proper distance as the cosmic event horizon is the light cone for the observer's location at an infinite time in the future. It puts the edge of the knowable universe at 63 gigalight-years, which means that we will never be able to see the light that was emitted by astronomical bodies that currently lie 63 gigalight-years from us.